Welcome to this MOOCs online video course Theory of Yarn Structure. In the last two lectures, we discussed about module 5 mass irregularity of yarns. We started with Martindale's basic assumptions, then through mathematical derivations we reached to Martindale's formula, which is well known to us. Then we found that Martindale's formula could not explain the mass irregularity of sliver or yarn very well. Two empirical corrections we discussed. One was given by Worcester company, which was purely empirical. Second empirical correction was given by G.M. Barnett, which was also empirical. However, it was based on a very nice idea of fibers forming clusters, those clusters forming sliver. However, G.M. Barnett's model has a problem. It could not explain the sliver or yarn formation when the number of fibers in the cross section is less than 64. That was the problem with Barnett's empirical correction. Today, we are going to critically review Martindale's assumptions, and then we will discuss a mathematical model on mass irregularity of sliver or yarn after incorporating corrections to Martindale's model. So, we will now discuss about Martindale's assumption. Martindale assumption, first he thought that fibers forming the slivers are straight, and parallel to sliver axis. Of course, this assumption is an idealized one. However, it is acceptable. The dominant tendency of fibers in the sliver are parallel to sliver axis. Second assumption of Martindale was fibers have same length. Again, this is an idealized one. However, acceptable, though we know that in case of cotton fiber, fibers have a significant variation in terms of length. However, in case of synthetic fibers, we can assume that fibers have same length. Third assumption of Martindale was fibers deposit randomly to form the sliver. Which is also correct. This assumption has an extension also, that is fibers move independently, individually, fibers move individually to form the sliver. This is not correct. G. M. Barnett already proposed that fibers form clusters, they have a tendency to form clusters, and those clusters ultimately form sliver. So, this assumption we will modify today, and we will discuss about a new theory, Nescar's theory, this theory is also known as bundle theory. So, this theory modifies the individual assumption of fibers in the sliver, and it imagines that a sliver is formed from aggregates of several units. Typically, these aggregates are hierarchical fiber aggregates. The lowest unit is fiber. The lowest unit is fiber, which is shown here, a single fiber. This unit is given a number 4. This lowest unit fiber form bundle. So, 2 or 3 or 4 fibers aggregate and they form a bundle. This bundle is given a number 3, unit number 3. Several bundles form a cluster. So, these clusters are given unit number 2. Several clusters form the ultimate sliver. So, the sliver unit is given 1. So, fiber unit number 4, bundle unit number 3, cluster unit number 2, sliver unit number 1. So, fibers from bundle, bundles from cluster, clusters from sliver. Now, in a bundle a few fibers are present. It is almost impossible to open the bundles into single fiber stage, because you can imagine imaginatively fibers are having glued or they are forming some knots to form the bundle. We know that cotton fibers have honeydew. So, they have a tendency to stick to each other, right, and also during processing, during mechanical processing, several fibers agglomerate and they form a bundle. It is almost impossible to separate individual fibers from a bundle. Those bundles form a cluster. So, cluster consists of several bundles, and it is possible by technological ways to separate those bundles from cluster by opening process. It is possible to separate those bundles from a cluster, and ultimately several clusters form a sliver. So, this is the hierarchical fiber agreement that this theory considers. Now, the creation of higher units from lower unit. Suppose from fiber to bundle, the lower unit is fiber, higher unit is bundle. So, fibers create bundle. This creation is random and independent. So, similarly, bundles from cluster, lower unit is bundle, higher unit is cluster. So, the formation of clusters from bundle is random and independent. Similarly, clusters from sliver, here the lower unit is cluster, higher unit is sliver. So, the conversion from lower unit to higher unit, that is from cluster to sliver, is random and independent. So, we write that the formation of lower units to higher units is random and mutually independent. Now, we would like to know about the numbers of lower unit in a higher unit. So, number of lower units in higher units. How many fibers form a bundle? How many bundles form a cluster? How many clusters form a sliver? Right. So, let us write in this column unit number and also in this row unit number. Now, unit name, so 2, unit number 2 means cluster, 3 bundle, 4 fibers. So, we write here cluster, we write here bundle, we write here fiber, and here we write 1, 2, 3. 1 is sliver, 2 is cluster, 3 is bundle. Now, how many cluster form sliver? This we denote by a symbol Q 2 1. This 2 stands for cluster, 1 stands for sliver. So, number of clusters in sliver is denoted by the symbol Q subscript to 1. Here the 2 denotes the unit of cluster, that is 2, and 1 denotes the unit of sliver, that is 1. Similarly, how many clusters from a cluster? It must be 1. How many clusters from a bundle from higher unit to lower unit? Not possible. Then how many bundles are present in a sliver? Q, first subscript is for bundle, stands for bundle, second subscript stands for the higher unit Q31. So, Q31 is the number of bundles in a sliver. Similarly, how many bundles from cluster? Q, first subscript lower unit, second subscript higher unit, and how many bundles form a bundle? Must be 1. Then the lowest unit fiber. How many fibers are present in a sliver? Q, first lowest unit 4, then 1. So, Q 4 1 denotes the number of fibers in a sliver, that is basically n, number of fibers in a sliver. Now, how many fibers from a cluster? Q, first subscript is lower unit 4, second subscript is the higher unit 2, Q 4 2. How many fibers form a bundle? Q, the first subscript lower unit, the second subscript higher unit. So, this is how we denote the number of lower units in higher units. Now, we will discuss about the mean numbers of lower unit in higher units. What is the mean number of fiber in sliver? What is the mean number of fiber in sliver? This must be equal to mean number of fibers in bundle multiplied by mean number of bundles in cluster multiplied by mean number of clusters in sliver. So, mean number of fibers in bundle multiplied by mean number of bundles in cluster multiplied by mean number of clusters in sliver, right, because these units consist only of fibrous material. Similarly, what is the mean number of fibers in cluster? So, fibers from bundle, bundle from cluster. So, mean number of fibers in cluster is equal to mean number of fibers in bundle and multiplied by mean number of bundles in cluster, right. Similarly, what is the mean number of bundles in sliver? Mean Q31 bar, mean number of bundles in sliver. This must be equal to mean number of bundles in cluster multiplied by mean number of clusters in sliver, right. Similarly, there could be maximum number of lower units in higher units. what is the maximum number of fibers in sliver? This must be equal to maximum of 3 units, that is maximum of fibers in bundle multiplied by maximum of bundles in cluster multiplied by maximum of clusters in sliver. Similarly, what is the maximum of fibers in cluster? So, this must be equal to maximum of fibers in bundle multiplied by maximum of bundles in cluster. Q 43 max into Q 32 max. Similarly, what will be Q, let us write here, maximum of bundles in sliver. So, maximum number of bundles in cluster multiplied by maximum number of clusters in sliver. Right. So, this is about the number of lower units in higher units, mean number of lower units and in higher units, and maximum number of lower units in higher units. Right. Now, we will discuss about the fineness of these different units. What is the fineness of bundle? What is the fineness of cluster? What is the fineness of sliver? This we are now going to discuss. So, fineness of different units. Let us first write unit number 2, 3, 4, then unit name, sorry, it must be 1, 2, 3, 4. So, the first unit is sliver, this is the highest unit. Second, cluster. Third, bundle. Fourth, fiber. Fineness. So, fineness of sliver, let us write T subscript 1. T stands for fineness and 1 is the stands for unit. So, basically fineness of sliver we generally denote it by capital T. So, T 1 is capital T here. Fineness of cluster, how to denote? T stands for fineness and unit number is 2. So, T 2. T 2 denotes the fineness of cluster. Similarly, how to denote fineness of bundle? T is a symbol for fineness and 3 is the unit number for bundle. So, T subscript 3. Similarly, fiber, the lowest unit, T is the fineness, 4 is the unit number. So, T subscript 4. T subscript 4 denotes the fineness of fiber. What is T subscript 4? That is equal to T, because we generally denote T by fineness of fiber, right. Then we will talk about CV of fineness. CV of fineness, we generally denote it by V, VT1, that is equal to VT, same symbol. then T 2 is the fineness of cluster. So, C V V T 2. Similarly, V T 3 is the C V of fineness of bundle, and V T 4 which is equal to V T is the fineness of C V of fineness of fiber, right. Now, let us define them. T 1, what is the expression for sliver fineness? Local sliver fineness, it can be 0 locally if there is no fiber or no bundle, no cluster. So, it is 0 for Q 2 1 number of cluster in sliver is equal to 0. If there is no cluster, fineness is 0. If there are clusters, then it must be equal to summation of fineness of clusters. So, I is equal to 1, I is equal to number of clusters in sliver for Q 2 1 is equal to 1, 2 and dot, right. You remember in the last module, this type of random variable we discussed is a type y random variable, y type of random variable, and you remember if this is the definition of a random variable, what will be the expression for its CV. We will discuss that later on. Now, we are interested to define T 2. T 2 can be 0 if there is no bundle. T 2 will be summation of T 3 I if I is equal to 1 to Q 3 2 for again this is also y type random variable, and we have discussed what will be the coefficient of variation of fineness of such quantity. Similarly, T 3 bundle, it can be 0 if there is no fiber in the bundle. Right, but if there are fibers, then it will be summation of fibers right. This is also type y random variable. Right. So, this is how we define the fineness of the higher units. So, fineness of bundle, fineness of cluster, fineness of sliver, these all are type y random variable. Now, we consider that the number of lower units in the higher units follow binomial distribution. So, number of fibers in bundle follows binomial distribution, number of bundles in cluster follows binomial distribution, number of clusters in sliver follows binomial distribution. So, there are 3 binomial distributions. Earlier we have discussed that in case of binomial distribution, the fineness of sliver is equal to mean number of fibers in sliver plus 1 minus n bar by n. You remember this formula we have discussed in the first lecture of this module. So, what is this? This is basically mean number. Similarly, this is also mean number and n is the maximum number. You remember we have discussed this formula v square t plus 1 minus p. This p is basically probability small l by capital L is equal to n bar by n, right. Now, this we will use in case of bundle, cluster and sliver. So, we can write v square t 3 square of CV of fineness of bundle is equal to 1 by mean number of bundles mean number of fibers in bundle Q43 into V square T, T1, T4, T4 is equal to T you know plus 1 minus mean Q43, Q43 max. Right. This is basically T4 and T4 is T. Okay. We can write it T4. So, that is basically T. Similarly, for cluster mean number of what? Mean number of bundle in cluster Q 3 2, right. Mean number of bundle in cluster, coefficient square of coefficient of variation of bundle plus 1 minus mean number of bundles in cluster divided by maximum number of bundles in cluster. Okay. Then square of CV of 1, square of CV of sliver 1 by mean number of clusters in sliver square of CV of cluster plus 1 minus mean number of clusters in sliver divided by maximum number of clusters in sliver. Right. So, this we can also write as v square t and this we can substitute by v square capital T, is not it? Now, what we will do? We will now write it together. So, here we will substitute this expression, then this will be substituted by this expression. So, it will be a quite long expression. So, let us do that. So, we write it again V square capital T. What is this? Square of CV of fineness of sliver 1 by this V square T 2 plus 1 minus this by this, right. So, we rewrite the same expression. Now, we will substitute here in terms of T 3. Right. So, if we substitute V square T 2 right. Plus 1 minus let us put a bracket for convenience. Okay. So, what we get? Q 3 2 Q 2 1 T 3 plus 1 minus this max plus Q 3 2 1 minus all right. This expression will be longer further, because we are now going to substitute here in terms of T 2 T 4. So, Q 3 2 Q 2 1 V square T 3 is V square T 4 plus 1 minus Q 4 3 bar Q 4 3 max divided by Q 4 3 bar plus what is remaining 1 minus Q 3 2 to max plus 2 right. Then finally, we write this expression Q 4 3 Q 3 2 Q 2 1 V square T 4 V square T 4 is V square T plus 1 minus Q 4 3 bar by Q43 max plus Q43 bar 1 minus Q32 bar max plus Q43 bar Q32 bar 1 minus Q21 by max. Right, this is quite long expression. Now, we can substitute here V square T square of C V of fiber fineness, and look at this Q43 bar mean number of fibers in bundle multiplied by mean number of bundles in cluster multiplied by mean number of clusters in sliver, which is equal to mean number of fibers in sliver, which is further equal to n bar, right. Then we can rewrite this expression by changing this. So, V square T is equal to 1 by n bar square bracket starts V square T plus 1 minus Q43 max plus Q43 bar 1 minus Q32 max plus Q43 bar 32 bar 1 minus by, and we close the square bracket. Okay. Now, what we do? We rewrite this expression in a little different manner, n bar. This one we write here. So, V square T plus 1, this one is here, right, minus, instead of minus let us write plus Q43, this Q43, let us take it common, and Q43 is also here. So, we can write 1 minus 1 by Q43 max, right, minus this bracket close. Okay. Now, what is this? Mean number of fibers in bundle multiplied by mean number of bundles in cluster. So, that is equal to mean number of fibers in cluster, mean number of fibers in cluster. Right. We now assume that this mean number of fibers in cluster is equal to some factor multiplied by mean number of fibers in sliver. So, this P is a measure of fiber individualization. P is a measure of individualization, right, and of course, P must be less than 1. Then we substitute here this quantity and we would like to rewrite what it becomes 1 by n bar into V square T plus 1 plus Q43 1 max minus this max bracket close plus P and Q41 bar is equal to n bar. So, P times n bar. Okay. Let us consider now this whole expression V square T plus 1 plus this is equal to A. So, this part we consider is equal to A and the remaining except n bar we consider as B. So, P multiplied by 1 minus we consider as B. So, then this expression becomes V square T is equal to 1 by n bar A plus n bar into B. So, that is what we write next. So, this equation becomes V square T is equal to A plus B times n bar divided by n bar. So, if we write in a standard form, V square T is this A plus B this by this, or V T is equal to this into A plus B T bar by T bar. So, this bundle theory under the assumption of binomial distribution leads to this expression. A and B are two parameters. Right. What is A? A is V square t plus 1 plus q 4 3 1 minus 1 by q 4 3 max minus 3 2 by max, and B is equal to P times 1 by divided by max, right. Now, a small note here. If these two maximum quantities are very large in number, then this fraction becomes small, this fraction becomes small. So, there is no problem in A. However, if this is small, then this fraction is very large. If this is very small, then this fraction is very large. Large quantities is subtracted from 1. So, this whole can be negative. So, V square t plus 1 can be less than A, right. All right. So, this is the final expression for sliver irregularity based on bundle theory under the assumption of binomial distribution. What will be the form of this under Poisson distribution? So, now we will discuss about Poissonian distribution. So, finally, we come to Poisson distribution. So, our assumption is the number of lower units in higher units follow Poisson distribution. So, in Poisson distribution, the maximum number of lower units in higher units tends to infinity. What does that mean? Q 4 3 max, Q 3 2 max, Q 2 1 max tends to infinity, and Q 4 2 max, Q 4 1 max, Q 3 1 max tends to infinity, right. Now, we come back to our previous one. Q 4 3 max tends to infinity, this then very small. Similarly, when Q 3 2 max tends to infinity, this becomes very small. So, these two fractions we can neglect. Similarly, so A becomes V square t plus 1 plus Q 4 3 bar. Similarly, when Q 2 1 max tends to infinity, this becomes very small. So, B becomes P equal to P. So, in Poisson distribution, this A becomes V square t plus 1 plus Q43 bar and B becomes P. So, the final equation is this, where A is this and B is equal to P, right. So, we obtained two important expressions under bundle theory, one based on binomial distribution, the other based on Poissonian distribution. Now, what we will discuss? We will discuss this theory with the view of Worcester statistics data. So, Worcester statistics 1997. So, you know that Worcester conducted a huge amount of trials in different spinning companies around the world, and they collected the data of mass irregularity versus count, and they plotted graphs called Worcester statistics curve. Very similar curves are here. So, this was in the case of carded cotton yarn. So, along the x axis fineness yarn, this was in case of yarn. So, along the x axis yarn fineness in text is plotted, along the y axis CV of yarn fineness dimensionless is plotted. Here you see there is for each one there are two dotted lines. So, if you remember, in Worcester statistics curve is a thick red line. This thick red line has one top surface and also one bottom surface and one middle one. The top and bottom are denoted by the dotted lines here, and the fine line is the middle of Worcester statistics curve, and the thick line is obtained from bundle theory. Statistical regression technique was used to obtain the thick line, that is from bundle theory. And as you know, Worcester defines irregularity in this manner: A and B are parameters, and this bundle theory V t is equal to by t bar A plus B this, right. So, this is the bundle theory. Then for different curves 5% of the spinning companies worldwide follows this curve, 25% follows the next one, 50% follows the next one, 75% of the spinning companies worldwide follow the next one, and 95% follows this one. Now, so these curves were used to find out these parameters small a and small b for Worcester and capital A and capital B for bundle theory. So, you see that for 95% for this parameter A was 0.35340, point B 0.20419, however, A 2.30832 and B 0.01615. Similarly, for different curves these values are given. What we can observe is that the value of B is very small, it is in the order of 0.0012 to 0.01, and the value of A is little more than 1, 1.56, 1.74, 1.99, 2.1 to 2.31 is like that. So, this is what we obtained in case of carded cotton yarn. How this bundle theory behaves or how this bundle theory is compared with Martinelli's theory, that we will discuss in the when we will talk about the numerical problems. Thank you for your attention.